Hello, Professor Dong. This is Sarbjeet Singh here with my colleague Emery, and right now we'll take two on the Fourier transform of linearity. First of all, the properties of linearity in Fourier transform states that a system is one in linear, has to obey the properties of superposition. Now, as for that example, my partner will give that soon, but I could give you a very concise definition of it, which means that if your input x of nt leads to output yn of t, then we could say that the output will resemble the input. You could do this in summation or multiplication. So if we add two functions, then the Fourier transform of the resulting function is simply the sum of the individual Fourier transforms that were used to put in the input. Also, if you multiply a function by a constant, then we must multiply the Fourier series by the same constant, as it will manifest in the output. Now, my partner is going to take over and he's going to do an example, and then he's going to do a derivation of linearity.
Alright, I just wanted to start out real quick and say that we had some tiny problems with the software. Couldn't record the video and the audio at the same time, so there might be a bit of a problem. So here we go. My name is Emery, and let's begin. The derivation of linearity. Consider the following two systems represented by f of x of t plus f of y of t. Now, as you can see, you have x of t of a, which then becomes ax of t, and you have y of t, b, which becomes by of t. Now, in linearity, a and b are constants that can be represented by any number. They don't directly affect the Fourier transform at all. Pretty much, it's when it comes to linearity, it's like as you read here, whereby superposition property we have final equation as f of x of t plus f of y of t, which is equal to ax j omega plus b j omega. I'm sorry, y j omega. The way it works is the constants don't really affect what happens in Fourier transform. So by introducing them in the beginning and at the end, they're pretty much the same. Let me see, what else is there? Alright, here we go. Moving on to the next slide. Proof of linearity. Alright, so consider the following two systems. We have x1, j1, and y1, and we have x2, g2, and y2. From these two systems, we obtain x1 is equal to g1 times y1, and we have x2 equal to g2 times y2. By linearity, we get the summation of ax1 plus bx2 is equal to ag1 times y1 plus b times g2 times y2. Pretty much by introducing the constants at the beginning, it doesn't, you would also, and it's like simple mathematics. By what you do to one end, you have to do to the other. Proof of linearity. Consider the following two equations. F of x of t minus x j omega, equal to x j omega is equal to the integral of negative infinity to positive infinity x of t times e to the negative jt dt. We have f of y of t equal to y j omega, which is equal to from negative infinity to infinity, y of t times e to the negative j omega t dt. Putting these two together, we have f a of x of t plus by of t. As I said, a and b are just simple constants that can easily be taken out. By separating these two, we get, I'll explain that. F a of x of t plus y of t. Oh, there's a parenthesis that doesn't belong there. Sorry. F b times y of t. So when we put these into, by separating them, now we can do the integral of each individual thing. So we have, which first we were going to do, though, is going to take the constants out, as you can see right in the next line. We have a to the radical of negative infinity x of t times e to the negative j omega t dt plus b integral of negative infinity to infinity y of t e to the negative j omega t dt. Finally, we say that these equal to a of x of j omega plus by j omega. From this proof, we can see that to prove the Fourier transform function in linearity, all we need to do is to take the linearity of the integral, which I will show in a later slide. Alright, so example of linearity. Consider the following problem and how we obtained solution. So we have f of 2 times e to the negative t times u of t plus 3e to the negative t times u of t. Now, as you can see, we split it up as we did in the previous slide, and then we take out the constants, and then we'll just show you the answer. In the next slide, I'm going to show you how to take the integral, or how to solve the integral, and then in the slide after that, I'll show you in the complete version of how to solve the entire problem. Now, particularly for these, what you want to do is, hold on, let's wait for this slide to change. Give me 1 second. Come on, move mouse pad. There we go. Sorry about that. All right. How to solve the integral. So as you can see, we're basically saying x of t is equal to e to the negative t times u of t. This is just solving the integral without any constants, and just showing you how it works. We have f of x of t, which is the integral of negative infinity to infinity, x of t times e to the negative j omega t dt, which by changing x of t to what it's equal to, we have negative infinity to positive infinity, e to the negative t times u of t times e to the negative j omega t. If you follow the arrow, you see where we go, the next line. And from here, what you want to do is you want to combine the two e's. By doing so, then you're going to have e to the negative t plus negative j omega t times ut dt. And now after that, what you want to do in order to complete the integral is you have to get rid of u of t. By doing so, you're then going to have to change the integral as well. So instead of going from negative infinity to infinity, you're going to go from 0 to infinity, as you can see in the next line. So we have the integral of you have the integral of 0 to infinity e to the negative t parentheses 1 plus j omega. If you take the t out of and put it in parentheses and for the power, it's a lot more simpler for the antiderivative. It makes things clear. And you have dt. Oh yeah, sorry, dt. So then from there, you want to take the antiderivative, which comes out to e to the negative t parentheses 1 plus j omega all over negative parentheses 1 plus j omega, and you have to solve the integral from 0 to infinity. If you know how integrals work, it's b minus a, b being infinity, and a being 0. Now, because it's e to the negative power, it's going to be 1 over that e. And anything to the infinite power is basically infinity. So it's 1 over infinity, which basically becomes 0. So as you can see there, so in the third line, so 0 minus 1 over negative parentheses 1 plus j omega, and negative negative equals a positive, so we have 1 plus j omega. Yeah, 1 over 1 plus j omega. And that's pretty much how you solve the integral. Now, in my next slide, I'm going to show... hold on, did I miss anything? No, I didn't miss anything. So in my next slide, I'm going to show you how to solve the example problem. I left out how to solve the integral just for saving space. So this way you guys can see it. Yeah, there you go. There was a previous problem. So like I said, I left out the integral so I could save space, and I wanted you guys to be able to solve it on your own. I just showed you how to solve the integral, so you wouldn't be lost. So here we go. We have x of t is equal to e to the negative t u of t, and we have h of t is equal to e to the negative 2t times u of t. So we're going to write that in Fourier transform. We have f 2x of t plus 3h of t, and like I said before, 2 and the 3 are just constants. So what you want to do is you're going to break up both the Fourier transform into two different Fourier transforms, and then you're going to take out the constants that you see in the next right as it equals to. So you have 2 f of x of t and plus 3 f of h of t. Alright, and then you're going to then you're going to do from the Fourier transform, you're going to turn it into an integral with the constants outside of the integrals, as you see there. So from there, pretty much you can see it's all straightforward. You just solve for the integral. As I said right there, insert work, you would just solve for the integral. And then from after that, you do the antiderivative, then you introduce the numbers from b and a, and stuff like that. And then pretty much there you'd have it. There's the answer. As you see in the previous line. It's pretty straightforward. Linearity is very easy. That's all I have. Thank you for listening, and I hope this was clear and educational for you. Like I said, my name is Emery, and my partner was Mr. Singh. Have a nice day.